In this example, our goal is to find the Thevenin and Norton equivalent circuit. So here's a circuit consisting of a current source, and our goal is to figure out the Thevenin and Norton equivalent circuit seen through terminals A and B. So here it is. Alright, first step, let's find the Thevenin resistance. To find the Thevenin resistance, goal is to zero out all sources. What does that mean for a current source to be zero? A current source of a zero basically means there's no current flowing through it, indicating an open circuit. So wherever we have the current source, we can replace that with an open circuit like this. Now in this circuit, looking for terminals A, B, our goal is to figure out the resistance seen from there. So we have 9 ohm in series with 36 ohm. That gives us 45 ohms. Now this total network of 45 ohms, is this network of 45 ohm is in parallel to this 9 ohm resistance. So we can write the circuits in parallel. This 45 times 9 divided by 45 plus 9 gives us 7.5 ohms. Now our goal is to find the Thevenin voltage. To do this, we can apply a number of different techniques. You can use whatever your favorite circuit analysis technique, loop analysis, node analysis, voltage divider, current divider, whatever you want. In this particular example, I will use the nodal analysis. That happens to be my favorite circuit analysis technique. Okay. So let's label the nodes. Let me call this node P, call this node A, and I've chosen a reference node right here. So here's my reference node. Now, applying nodal analysis, before we do that, let's draw the direction of the current and apply nodal analysis. Basically, this shows current coming out of node P going to the 36 ohm resistor, current coming out of node P going to the 9 ohm resistor must equal the 3 amp resistance. So applying KCL at that node, I get the following. Similarly, applying KCL at node A, this current right here is coming in, and that current right there going down the 9 ohms. So those must be equal. So applying KCL, we get. You can use a calculator, MATLAB, your hand to figure out what the values of VP and VA is. In my case, I like using MATLAB. So using that, I got VA is 18 volts, VP equals 36 volts. There's a way to check if that's correct. Now if you look at this point, A is in midpoint between P and ground. There's two equal resistance 9 ohms. So there must be equal voltage drop in the 9 ohm resistor that's here and the 9 ohm resistor that's here. So VA, which is the voltage drop across this 9 ohm resistor, must be equal to 1/2 of VP, which is the total voltage drop across this resistor and this resistor. Okay, so 18 is half of 36. So that lets us know that we're correct. So Thevenin voltage is VA because that's what is seen from the source. Now for the Norton current, it's basically the Thevenin voltage divided by the Thevenin resistance. So we get I Norton is equal to VTH divided by RTH, and that gives us 2.4 amps. So here's our Thevenin equivalent circuit with 18 volt source, 7.5 as seen from terminal AB. So if I'm looking at this way, it can be approximated as a 18 volt source with a 7.5 ohm resistor in series, or as a Norton equivalent circuit, which basically means a 2.4 amp current source in parallel to a 7.5 ohm resistance source. Let's do one more example. For this circuit, our goal is to figure out the Thevenin equivalent circuit and the Norton equivalent circuit. Again, let's start out by finding the Thevenin resistance. In this case, we'll zero out the voltage source. Voltage of A equals 0 basically means two nodes are at the same potential. That basically indicates a short circuit. So we replace a voltage source with a short. Now doing that, we see that the 10 ohm and this 10 ohm are in parallel. We see the 30 ohm and that 30 ohm are also in parallel. So we can write this as 10 and 10 in parallel gives us 5. 30 and 30 in parallel gives us 15. And now we see 15 and 5 are actually in series. 15 and 5 are actually in series, so we get 20 ohm in parallel to 30 ohm. And if we simplify this, we basically get a total Thevenin resistance of 12 ohms. Now, finding the Thevenin voltage, again, use your favorite technique. In my case, I'll use nodal analysis. So let me label the nodes. The reference node is already here, so 64 volt across, so that means this point right here is equal to 64 volt. Call this node P, and I'll call this node Q. So let's draw the direction of the current and basically apply nodal analysis. So current coming into node P is equal to current coming out. So 64 Vp over 10, so that's the current going down, plus 64 minus of Vp minus Vq divided by 15, which is this, equals current coming into the node, which is 64 minus Vp divided by 10 ohms. Well, that gives us, if we rearrange everything, we get the following equation. Similarly, we can write KCL at node Q. Node Q, we have current coming from P towards Q through a combined resistance of 15 ohms. So Vp minus Vq, current coming in, minus Vq divided by 15 is equal to Vq minus 0 divided by 30. Rearranging that, we get this, and if we use our favorite technique to solve the two equations, we get Vp and Vq values. Vq comes out to 19.2, and that happens to be the Thevenin voltage. Now, finding the Norton current. Norton current is Thevenin voltage divided by the Thevenin resistance, so we get 19.2 divided by 12 equals 1.6 amps. So again, here it is for this circuit. For this circuit, here's our Thevenin voltage, 19.2 volts in series with 12 ohms, 1.6 amps in parallel to 12 ohms.